Hey guys, so I've been very busy in the last few weeks, months. I can't really even remember when the last time I posted a YouTube video was, but I do have some updates. And I'm gonna start off with what stuff I have found at my various sources, let's call them that, and I'm going to talk you through a bit through some of the more interesting stuff that I have received. I've actually gotten a few gifts as well from some lovely people, and I'm going to mention all of that a bit later. But we're on the other side of the lab. Let's call it a lab. And I have a small stack of stuff here. I'm gonna show you the rest of it in just a bit, but this used to be a almost floor to ceiling high mountain of test gear, which now resides in the balcony, which is that way. So you're actually seeing natural light on the surface of these things, so I hope the video is going to turn out pretty well when colors and stuff like that. And without further ado, let's start. Oh, by the way, I moved most of the test gear that I had here, which was repair projects and stuff. I repaired a LaCroix Wavemaster 24 for a friend of mine. It powered on, but then promptly shut itself off when it tried to start up the oscilloscope application. So I took it apart, which took about 45 minutes because it's got a gazillion screws. I'm gonna try and insert a few photos here if I have them. And the issue was that the main, I think it's either the ASIC or for data processing or something. So on the board there's 3 heat sinks, two symmetrical ones and one in the middle, and retainer clip for the heatsink on that one had snapped from the board, so it had ripped from the holes. It's one of those inverted U-shaped things soldered. It's 2.1 inch pin headers, 3 spaces, all in all, so there would have been another 0.1 inch header in the middle, and they just form a hoop, and the heatsink retainer snaps through those, and it just ripped off the board. I soldered it, and added a mountain of solder on the other side to make sure that it wouldn't release again. And I also touched up the solder on the other side. I don't know what made it break like that. And I said I don't have a picture, but the corner of the die was actually chipped, and I thought, no way is this gonna boot, because the heatsink had been flapping in the breeze and probably hit the edge of the die in shipping and damaged it. But apparently it didn't hit anything important because everything worked perfectly on the oscilloscope. So that was that. So let's start with this thing. I'm not gonna take it apart or move it from there because it weighs a insufferable amount of kilos, and it's not plugged in because it's got one of those weird what do you would call it? I don't know. It's an old German DIN style of connection on the back. And what is this thing? Well, I think you could kind of tell by looking at the voltages on the scales on the terminals binding posts. So we have 4 volts, 6.3 through to 12.6, and we have 150 volts and 15 volts negative, and 0 to 300 volts at 3 amps, 0.3 amps, sorry. And this thing is a statron, something like that. I'm not gonna try to pronounce this, but it's a stabilized power supply made for working on vacuum tubes. So we have the filament, a couple of bias supplies here. They're not meant to handle a lot of current, so these are just a couple of, I think one of them is a transistor and the other is another small vacuum tube. And this output actually comes from 4 EL34 power pentodes, all in parallel. And there's a great big honking transformer inside around here. And it's very nice because all the boards inside are mounted like in a Eurorack style system with plug-in connectors, so you can take all the boards out, work on them, and put them back in. So the first time I turned it on, it immediately started spewing capacitor smoke, which was stupid on my part. I should have recapped it before turning it on, but after I recapped it with some of these and some off-brand Nippon Chemicons, because I've been informed that these are not actually Nippon Chemicons, they're off-brand. It seems to work just fine. It can turn resistors into light-emitting resistors, and it's got a clunky voltage setting thing, so you can set it quite finely, and there's even, this one's a potentiometer actually, so there's 3 decades and a potentiometer for fine-tuning up to 30 volts or 24 volts. So yeah, that's about it for this one. It still needs a bit of work. I have to clean it up a bit more. It was full of cobwebs and spiders and dust and stuff like that, and I think a couple of the twin triodes inside are a bit weak, because I'm not pretty sure if they might be either weak or they might have been leaking a bit of air. Getters on them still look fine, but something's fishy about this thing, so I'm gonna clean it out a bit better, and hopefully I'm gonna use it. And I also need to do something about the handles. They're kind of, at least one of them is kind of rusty, the other one is pretty nice. So that's about it for this. Let me reframe and I'll show you a bit more. So this is actually not new. This is very old. It's a 510 model lock-in amplifier by Stanford Research. And I have another piece of Stanford Research equipment behind me, which we'll get to in just a second. This was a repair project that was very frustrating, and I didn't film it because I wasn't in a very good mood, and it's kind of old at this point. But what was wrong with it was that there were like 15 dead tantalum capacitors inside. I might have mentioned this thing in a previous video, I don't know exactly. 15 dead tantalums and a couple of chopper amplifiers which were completely dead. Same chopper as in the Solartron that you saw last time. And this is a Tektronix, I think. It's a Czech or Polish DMM. It's 3.5 digits, but it's very, very pretty, and it's measuring a resistor right now. It's 100 ohms. This was actually fully working when I got it, and I paid by the pound for these things and a lot more stuff I'm going to show you in today's video and in a future video. It's actually a very nice little meter for bench use and stuff like that. So it's very, it's a 3.5 digit meter, but it's got everything you need. I'm debating whether or not I should, you know, give it to a student or something like that, but it's kind of pretty to look at, so I might keep it. And it's very, very small, so it's about this deep. So very pleasant form factor. Here we have a 7L5 spectrum analyzer plugin for a 7000 series mainframe, which you might be able to see around here. We're going to get to that. It's missing the all-important input module, either the L1, L2, or L3. So this is a 5 megahertz spectrum analyzer. It's got built-in storage. It's very, very nice. I'm going to actually, I think I found the source for a L3 input module. It won't work at all without that, and what's more frustrating is that the input module contains the actual attenuator and mixer for the thing, so it's pretty much not a spectrum analyzer without those components. But this comes from Dennis, along with the mainframe, and he's a very, very kind guy, and he actually has a very interesting job at the PTB, and he was kind enough to send me a letter, which I'll show you a bit later, along with some more stuff that he sent me. So let me reframe again and show you the tech mainframe and the thing you're seeing here. Right, so this is a 7603 oscilloscope mainframe. It's very nice because it's got one of those giant displays on it. So the screen on it is about 10 by 10 centimeters across. So it's one of the biggest ones on any Tech 7000 series scopes. It's trying to trigger because I don't really know how to use these oscilloscopes. I've never really owned tech scopes, and let me tell you, I'm a convert now. It's got 3 bays, one of which is full of tunnel diodes. We're gonna get to these in a second. And this is a 7A18 and a 7B50, so just a regular time base and 2-channel amplifier. So you can have a 4-channel scope or a spectrum analyzer or digital multimeter or anything. You can have every sort of plug-in slot into these things. Tektronix even made a 7000 series optical spectrum analyzer with a monochromator diffraction grating inside, sorry, and it could do optical spectrum analysis, which was pretty cool. Apparently they only made like 20 of those, and that would be a really cool plugin to own, but yeah, probably they're very, very long gone by now. It's a beautiful scope with a beautiful screen, and I like the fact that you can change the intensity both for the traces and for the readout. It's a single beam oscilloscope, I think, and I'm not entirely sure how they do this, but they seem to get a bit brighter when so the readout gets a bit brighter when the spot is next to it, so it might be chopping them, or I don't know, drawing them in between the sweeps, so not entirely sure about that. But so I have sort of got a source for the L3 plugin for that one, and we're gonna test it out when I get it here. But this one actually arrived a bit damaged in shipping. There was a PCB inside the vertical amplifier which was not seated correctly. Probably got smacked around despite the excellent packaging Dennis used, and I reseated it and checked a few of the tantalum capacitors, and everything was fine. And you can, this is another thing that I really like. The gradical intensity goes from you don't know there's a gradical there to not very in your face, but you know, and this is the beam finder basically. And it's got a calibrator and everything you need in an oscilloscope, so it's a very, very, very nice unit. Okay, let me move you around again so we can talk about the thing on top. Right, so we have another beautiful old piece of test gear, completely, well, not quite completely obsolete, but not very high performance. But this is a collectible, in my opinion. It's the famous Telequipment CT71 curve tracer, and it goes up to 1000 volts and 10 watts peak of collector power, and it can test anything: resistors, diodes, MOSFETs, JFETs, bipolar transistors, etc., etc. I even tried testing glow discharge tubes like neon indicators and stuff like that, and they oscillate like crazy. And I'm gonna try and show you a bit more in detail about this thing in a future video. But I have two applications that I wanted to show you. For example, so side bracket. I got it with this knob broken, and this knob is actually kind of important because it sets the drain or collector resistor. So the way this thing works is basically voltage is on the horizontal scale and current is on the vertical scale, and you have a collector supply which you can adjust here. It's actually a big rheostat back inside the instrument, and you, depending on the settings of the volts per division and the collector resistor, you can get more voltage basically on the supply. This is basically the percent of the maximum voltage. So if you multiply the reading on the scale by 10 divisions, you get the max voltage that you can apply to the component when you're testing it. So for example, if you're on the 100 volt per division, there's 10 divisions, so you get 1000 volts of output. And this knob, as you can see with the small window, actually sets the collector or drain resistor in this case, and it allows you to, well, look at various regions of operation for the components you're testing. So we're looking, for example, now at the triode region of a JFET. This is basically the where it's most non-linear. So I'm a bit tired and I can't really explain this properly. We're going to go into more detail a bit later in a later video, but I have taken the measurements out of what was left of the old knob and a bit of guesswork, and I've actually come up with a design that I'm pretty happy with. It took a couple of iterations because the first one, the window wasn't big enough, so I couldn't see the resistor reading properly. So this sets the steps, so you can have up to 10 steps, and you can see that it's really being like, this would be saturation if it were a bipolar transistor, but this is the you know, this is saturation here. So you can change the number of steps from basically 1 to 10, and you can change the polarity so of the steps, so more positive or more negative, and you can move it around, you can shake it all about, you can do the hokey pokey. Jesus, it's stronger than me. And I actually took the time yesterday and calibrated this thing against the 7603, which I kind of trust. Anyway, it doesn't really matter. And it has two sections, so this is pretty useful for matching transistors. So you can see there's a very slight change in the shape of the characteristics of the transistor. So, and if you smack this switch in the middle, you can open the thing and look at your components. So I'm testing this matched JFET in there. And let me quickly pause the video while I remove this carefully and stick in a firm favorite of mine, which is the tunnel diode. I'll be right back. Right, so Osmu hoodie. There's the tunnel diode. It's in here. I think you can barely see it. And this is the weird characteristics that I was always talking and raving about. So if we look in a bit deeper, you can see barely there's two traces there. So it means that in here, in this region, there's oscillation going on. There's actually oscillation happening due to the effect of the the resistor in series, which is here, and the diode's nonlinear behavior. It's very so the negative resistance, the negative differential resistance of the diode on this slope here, in conjunction with the resistance in series, actually makes the thing oscillate. So it's very easy to see, and it's only showing up this wide and without any traces in the middle because of the bandwidth of the circuitry inside. So whenever you see a characteristics of a semiconductor tunnel diode and it looks like this, that's one of the characteristics. I also made the mistake of saying that you can actually measure the characteristics of a tunnel diode, and technically you can, but it's never truly the characteristics of a semiconductor tunnel diode. So yeah, so that's about it for this side of the lab. I hope you like this. This thing is so cute and I really love it. It makes me happy just having it. I've been wanting a curves tracer for ages now, and the 4145 didn't really scratch that itch because it's not as tactile as this thing is. So, you know, I'm still looking for a Tektronix 576, but that's at least 3 times the size of this thing. So, yeah. Okay, let me move you around to the other new side of the... It's not the new side, it's a new stuff. Let me show you more new stuff. By the way, before we move from here, let me show you quickly this beauty. Oh, I might need to reframe. You get the point. I'm going to show this in more detail. It's a very pretty vintage moving needle voltmeter, and what I like is that they used to respect their jobs and actually show you the linearity of the meter. So, and it's in a nice compartment underneath the movement. So yeah, okay, let me move you around and we'll talk about more stuff. So sorry about the awful image quality and the soldering tip changer. I have not one but 2 more Tekscopes. I'm going to show you the other one right after this one. This is a 466 analog storage oscilloscope, and it's got everything you could ever want from a scope. I'm sorry for the image being blown out, but storage means it's got a storage tube. So it's got the all the persistence display, and I'm not entirely sure how this thing works, but I do know how the analog storage works. So basically what happens is this is now captured a sweep, basically one sweep. So what happens is there's a mesh right before the screen which gets energized, and then the scanning gun actually draws across that mesh and charges some of it. And there's a couple of flood guns which just they're like floodlights but for electrons, and they just spray electrons at the screen. But where there isn't any charge from the scanning gun before, there's no way for the flood electrons to pass through, so there's no image. So that's how this works. I'm sorry if the explanation has been a bit off, but I'm going to insert the Wikipedia article in the description so you can see it more in detail. What it's doing after a specific amount of time is it's refreshing the storage. So it's doing the same thing. It's discharging the grid, scanning it, and then using the flood guns to make an image, basically. So, by the way, this thing hurts the tube, so you're not meant to use it for a long periods of time in storage mode, but you don't need to because you're looking at a non-repetitive signal and you want to take a minute to analyze it. This is one of the beautiful 460 series scopes. They're all kind of in the same form factor. 2-channel 100 megahertz. This was pretty dead in the same sense as most Tektronix oscilloscopes this age are. Dead tantalums and doo-doo in the switches, as a friend of mine said. So the attenuators on this one were pretty fine. There's one which is improperly tuned on the top channel on one of the ranges, so I have to get in there and try and get the right angle, fiddle with it a bit, and adjust the response. But this one actually also had a dead tantalum on the 15-volt rail and a de-socketed, semi-de-socketed transistor somewhere. So I just poked around with my fingies, and when I touched one of the transistors, it sprung back to life. So yeah, the things to look out for are usually dead transistors or de-socketed transistors, because the sockets are not very great and they oxidize over time and stop making contact, basically. And tantalums, yeah, all the tantalums are suspicious. And I need to reframe again so I can show you the other 460 series scope that I have. Wait a second. So terribly sorry about the backlight. It's the best I can do right now, but it's not going to be very much to talk about. This is the baby brother of the 466. It's the non-storage version. They do all have the delayed time base, which is very interesting because we have basically a time loop, and you can mix and match sweeps, and it's really black magic. So by turning this knob, I'm looking at a portion of the waveform, and I can look in more and more detail. So I can just look on, for example, at the falling edge, and can see that the response isn't really compensated on this one either. It also has the DMM 44 as the bottom one. Both of them work perfectly, but this one actually has something even cooler, the one on the bottom. It has the original temperature probe with the LEMO connector on it. So you can see that it's a temperature probe and it's isolated, so you're meant to debug circuits by, sticking the probe on stuff and seeing if it's hot or cold. And yeah, it's actually a very, very nice probe. You might also be able to tell that this is not original. The frame is not original. It's a 3D print. I managed to fix my 3D printer in the meantime, and I've been printing the hell out of a lot of things. And I just had a broken extruder and stuff, so it was quite an easy fix. I got the dimensions from YU. Thank you very much. I think he gave them to me, and it was a quick CAD job. It's just a simple part with a couple of fillets and a chamfer here, because I'm not gonna say it. Chamfers are nice, and a couple of fillets as well on these sides, just to make it look as much as the original as possible. I didn't include the what do you call it, the gutter, the complete brain freeze. There's a feature here which helps you lock a camera on it, but not having any cameras for this particular scope, you know, I don't really need it. And I made a couple of these extra for some friends who also have scopes like this with the frame missing. Right, let me reposition again and show you more new stuff. Oh, by the way, most of these things I fixed. The only things that actually worked from the get-go were the multimeter and the CT71, the curve tracer. Rest of them, I had to do some stuff to them. Like, for example, this one had misbehaving DMM, so I had to fix that as well. It's a 3.5 digit meter in the DMM 44, and it's got also a frequency counter on it, so it's very good for general troubleshooting. I rarely turn on the 3104 when I'm debugging, because I can use these two very easily. They're stacked on top of each other, and the storage scope, because of the longer tube, is a couple of inches longer than the regular scope. Right, so in the news around here, we have, let's start off with these because it's kind of easier to get. We have 3 reference resistors, 0.1 ohms. This one's 10 ohms. It might not look like it, but trust me, there's a 1 before that 0. A standard 0 ohm resistor would be actually kind of useful, but you know, superconductors exist. And this one's 10K, so I have 10K and 10 ohms, and provided these are any good, they should be, and alongside the 731 Fluke, I can actually do artifact calibration. Not very well, mind you, but I can do artifact calibration. The big behemoth in frame here is a FFT spectrum analyzer, also known as a dynamic signal analyzer. It's of course made by Stanford Research Instruments, Stanford Research Systems, sorry, and it's fully working. I got it off of eBay for, in my opinion, a steal, and I'm gonna use it to measure the noise of my of the front end for my ADC. And as you can see, we'll go into more details regarding this instrument in a while. So we've touched upon those, we've touched upon this. This works, as you can see. It's very, very nice to use, and the green display just gives me a warm and fuzzy feeling inside. And you might see this guy. This guy's completely new. New to me at least. So this was donated by a friend. Hi, Razvan. You've heard him on the first podcast. He asks me, look, I got a 8840 that I needed the LT Flu from. Want to do anything with it? And I says to him, of course, send it my way. And alongside this and some sweets, he also sent me some stuff to measure with my 3458 and the Solartron, which is going to him for an indeterminate period of time. So this thing was missing world-class voltage reference from inside. So I took a couple of looks at the schematic. I thought to myself, I could use one of these. It's one of those 1N825s or whatever. Very nice, very aged voltage reference. I have a few of these out of undisclosable source. I've put it in the circuit. I had some precision resistors lying around. Didn't really need them to be that precision, but you know, bypassed the control loop for the Zener current, and it didn't work. It wouldn't self-cal because the voltage was too low. So it was raising some errors because the ADC reading was too low for it to calibrate itself. I was calibrating it with this, by the way, so that's why the readings are so perfectly similar between themselves. So, then having a few LM399s available, I just piggybacked a 399 across the power pins of an op-amp that was in the reference circuit basically. So I'm feeding it plus minus 15 volts, and I'm using it to generate negative 6 point something. I managed to get lucky with a almost 7 volt LM399. And then I went through the calibration procedure for this, which is just sticking a screwdriver and pressing a button inside there. And you have the ADC calibration, where I used a very warmed up 237 to spit some voltages into it, and then you can calibrate the rest of the ranges. For the ohms, for the current, it was kind of easy. I just used the source meters again. I didn't calibrate the 1 amp range because I don't really need it, so I just gave it 1 amp from one of the power supplies. I trust this one quite a lot, so the reading was more than adequate. For the ohms, I used my decade resistance box that I found at the flea market, and it was adequate. So I have measured the 10K, the metrology reference 10K, using this, and it's pretty much bang on 10K. So yeah, I'm gonna insert a picture from the innards of this thing and show you the horror that has been committed inside of it. So it won't be as good as a LT flu, of course, but it's not gonna be far off, and it's only a 5.5 digit multimeter. So, and for a bench DMM, this is pretty great. Like, I trust it a lot, and it's very, very stable. I've measured the SMU is heating up now, so it's warming up. This thing is on completely. It's silent. It hasn't exploded yet. It has a Schaffner filter in it, which I will change. But I'm not gonna show you inside right now because I would need to turn it off, and being that it's turned on completely and warmed up, I kind of want to have it like that, so you're gonna have to settle for a picture. Another thing that I recently got was this, and maybe we'll do a video about it at some point. This is a Romanian-made temperature controller. It's got a heat and a cool, and you can set the temperature using these things. And it actually, if you use the PT100, it has a PT100 input on the back, and you can see there's a PT100 screwed down there. It can read up to 1600 C with a specific, no, it's a platinum rhodium, sorry, PT100, so, you know. Actually, I think it's a thermocouple, platinum, rhodium. I think it's an oven controller or something like that. So, but it wouldn't explain why it has a two-way contact, so for both heating and cooling. I don't know. Anyway, and it has the cold junction compensation, so it probably is a thermocouple. I'm pretty sure that that is not supposed to be a PD100 now that I think about it more, and it's also got a 4 to 20 milliamp current output. So I've corrected myself and made a fool of myself all within the span of a couple of sentences. That's what finals seasons tends to do, because yeah, that's basically why I haven't done any videos. It's been final season and I was busy with the university stuff. Successfully passed all my exams, by the way, with very good grades. Not that I care that much about the grades, but anyway, last two items. One of them more interesting than the other. Actually, let me reframe again and prepare some demonstration. I'll be right back. Right, so the first item that I have to show you here is a Honeywell. I think it's one of those golden gnats. So this is a gyroscope, and anyway, while it spools up a bit, let's talk about it. So this came out of it came off of eBay, of course. It was in a gyroscope unit for a plane, and it had two twin brothers, so for redundancy they needed 3 gyroscopes to do the reading. So yeah, I just took it out, measured some pins, and I got lucky. These things need basically 2 sine waves 90 degrees apart to run, and I have one of those cheap Class D amplifiers, and I'm feeding it with the signal generator, and it works. It does precess, and it's not the strongest gyro because it's, you know, it's a sensor, but you can see that it's kind of resisting me turning it around and stuff. And I really like how cool it looks, actually, and how beautiful it is. I did smash one to pieces just to see what was inside of it. So it turns out that the gyro motor itself is inside 2 layers of machined copper and brass and stuff like that, and the whole thing is full of very fine oil, and it even has one of those expansion bellows to compensate for varying temperature and pressure, so it doesn't explode because of the oil expanding. So basically that's so gyro, aircraft gyro, kind of hard to demonstrate. You need to feel this. I wish this was a feel-of-vision, but you can see that if I twist it a bit off to one side and let it fall, it behaves a bit like a gyro. Right, let me stop this and show you the last thing, because yeah, we're getting on to 45 minutes right now. So quite a complex setup, but this is a YIG-tuned oscillator, and it's from Dennis as well. and we're looking at the spectrum analyzer. I'm gonna actually set the amplitude a bit higher, so the reference level, because the output power of this thing is pretty strong. It's already got an attenuator on it, so it wants 15 volts, which it will shortly get, and it's drawing about 65 milliamps, and it's not oscillating yet. So if I give it 70 milliamps, hopefully we shall be able to see something, because I'm feeding it into the tuning coils. Let's turn off the menu. Oh, yay. We need to give it more like 100 milliamps. Right, so this is 100 milliamps from the SMU, which is about as much as I can give it, because, you know, it's a 100 milliamp SMU, but you can see that if I turn it down, it changes frequency until it doesn't oscillate anymore. And that's all I can have. So it's from 2.072 gigahertz to around 1.856 gigahertz. I think it's meant to run at quite a bit higher current, but I don't have enough spectrum analyzer to look at it any more than that, and I need to feed it a lot more current. And you can also, let's try this out. There's a thing called the FM coil on it, which is basically another electromagnet, very small electromagnet, very close to the YIG ball itself, and it affects it the same way as we're doing right now with the, you know, the current in the main tuning coil, but to a much smaller extent. So what's happening is there's a it's not an oscillator as much as a YIG-tuned filter. There's a small yttrium iron garnet sphere inside, in the middle of a magnetic field, which is generated by the tuning coil and the FM coil. The tuning coil is large and in charge, and the FM coil is very small and in very close proximity to the YIG sphere. And there's a transistor oscillator, and the output frequency is tuned by altering the properties of that YIG sphere using magnetic fields. So I'm going to try and see if we can see any modulation on the actually, let's go to span. Let's move the reference to center and span much smaller, and you can see it's not very stable because it hasn't warmed up, and it's still moving around a bit. So the current from my SMU is pretty stable, but this needs to be synthesized in order to have the best performance it can. And let's see if I can actually modulate this thing. Frequency. Yes, I can. So I'm feeding it 1 hertz, and you can see that the frequency is actually moving around by 1 hertz. So apologies, my signal generator was turned on. It's still bouncing around a bit, but not as much. And if I increase the amplitude, we should see that the frequency range that we're modulating is larger. So I'm gonna give it some time to sweep properly. So Per division, we have a 20 megahertz span, so we have about a 2 megahertz per division. So we're using a 1 hertz sine wave into whatever resistance that is, gives us whatever current. So we're getting about the 2 megahertz swing. Now that's more like a 2 megahertz swing. So I'm sorry about the brevity of the experiment, but I'm really also pressed for time, but very, very tired as well. But I had to show you some of the stuff that I have and some of the things that I've done and played around with. It's mostly been like short repairs over the weekends to relax and to, you know, just think about something else other than the subjects I had for university. So, by the way, those sidebands, I have no idea where those are coming from. I am not an RF guy, and I'm pretty sure that although there's a reasonable explanation for the sidebands, probably something to do with mixing. I'm not entirely sure. I'm pretty sure that this YIG is also not 100% functional, but come on, we made a 2 gigahertz FM transmitter in 5 seconds or something like that. So this is very cool. Like, technology wise, this is incredible. Right, so before I completely exhaust myself, I shall thank you for watching 50-ish minutes of me talking senselessly about varying subjects of varying degrees of interestingness. I think Marco Reps has gotten a better oscilloscope in the meantime, so he won't mind me having stolen his. Thank you for watching, and let me know if you want to discuss anything that I've presented in more detail, more sooner. And that's about it. Have a great day and see you soon, hopefully. Bye.